put out a review sheet before that, of course, but you can bring in questions and spend the day doing that. I'm pretty sure you're going to ace the midterm, and then it's up to you whether you want to come. I won't be giving any secret answers that I guess you always talk to your classmates if you're worried about that. Okay. So we're working now on, in the book, section 5.2, which is titled Definite Integrals. We talked a little bit about this on Thursday, this idea of looking at the area under a curve, breaking it up into pieces. The book defines it slightly differently, which I'm going to kind of go over, but you just say the details in this class are not that important. The book does is it says, all right, we've got some function, and we divide it up into the area under it into these call them slats or what have you, and they each have some area associated with them. And we estimate this area as a sum where n is, we've broken it up into so many of these slats, each of which has a width of delta x. And we just, this is where the book kind of differs in what I did. They use this symbol x star. X star just means within this area here, they pick some number. They're not specifying. It could be the average number, it could be the starting number, the ending number. But they don't need to be more specific than that. And then what we do is we add the limit as n goes to infinity. In other words, as we break this up into smaller and smaller pieces. And that's our estimate for the area under this curve. We have a notation that I think you mentioned. This is A and this is B. We use this integral sign. And I know I've gone over this, but I think it's worth looking at again. This elongated S is indication that we're doing some kind of sum. A and B are the limits going from A to B under this function. F of x, of course, is the function itself that we're dealing with. And the dx is just notation. If you go on in calculus, in math, sometimes this function could be a function of multiple variables, and this x here tells you what exactly we're integrating over. And this object here is called a definite integral. And although I've mentioned it before, it's good to keep in mind that this is a number. And like I said, 5 plus 7 is a number. It's not an equation. There's no variable involved. The x here is a dummy variable. I could rewrite this as A to B of f of t dt, it's the same thing. In a particular problem, you might want to emphasize, like if you're integrating some velocity over time, you might want to integrate, you might want to use the variable t just to indicate that it's time involved. But once you calculate the integral, these dummy variables go away. So, all right. We would like some way to evaluate this without going through this process of breaking this up into pieces, summing it, and then somehow finding a limit as these get smaller and smaller. That would be a very complicated problem. So to do that, we're going to look at some examples and try and draw some conclusions. So the first example is very simple. Our f of x is just going to be some constant c. So we have some constant c here. We have a and b. And so we're looking for the area of a rectangle. And our area is very easy to calculate. It's just the distance on x, which is b minus a times c, or bc minus ba. Now, as we go on, we're going to need some notation that we're going to use. So we might rewrite this as in this manner. Either we could write it as xc from a to b. X here is the variable, and what this notation says is that we want to calculate this. In other words, BC minus BA. We also might write this as, we might put it in square brackets, XC BA. And again, we're evaluating this expression here at B and subtracting the expression at A. Now, just catch up here. It's worth noting at this point that this function xc is such that the derivative of f of x, capital F of x, is just this, the function. Or to talk about it in the forward direction, if I take this function, I find its antiderivative here, and I evaluate it this way, I get the answer I'm looking for. Well, that's just a simple example. We don't want to draw a conclusion quite yet. Let's try a somewhat more complicated example. Let's take the function f of x equals x. All right, everyone knows what this looks like. Straight line to diagonal. And we have a here, here. So looking at this, we want to think about, well, what would the areas what is this area here between A and B? Well, look at it as a trapezoid, but I think it's easier just to see this as, we have some triangles here. We have a little triangle and we have a big triangle. And because f of x is x, this point is A, this point is B, so this big triangle here is 1/2 the square. We have a square here that's b by b, so it's b squared, but the triangle is half of that. And that's this entire triangle. But if we want the area, we need to subtract the little triangle. So that's a squared over 2. So that's our area. Well, again, we can use that notation I described. This would be x squared over 2 from A to B. Well, again, though, if we express this as this capital F function, you can see again that the derivative of this function is just equal to f of x. Or again, in reverse, if I were to take this function, I want to find the area under it, I would find its antiderivative, squared over 2, and evaluate it between A and B. Well, we have 2 examples where this seems to work. Right? But that just suggests we want to look at it more closely. But it certainly doesn't make it so. So we would like a little more confirmation. This is the harder part to follow. We start by defining a function, capital F of x, as follows. We define it as the integral here from a to x of f of t dt. Now, this gets a little tricky here. This is no longer a number because it's got an unknown variable. It's a function. And I'm defining this function as, take this function, whatever it is, and find the area under it from a to some x. All right. Having done that, I want to look at a particular construction here. You'll see the justification for this in a minute. I want to look at the limit as h approaches 0 of f of x plus h, is capital F, minus capital F of x over h. That should look familiar. It's the definition if I wanted to find the derivative of this function. All right, well, we need to investigate what this actually is, though. And we're going to do this graphically. So we're just going to put our a here. It doesn't really matter where it is. And we have our function f of x. And we have some point here, x. And a little further down, we have some point x plus h. Okay. So this first f of x plus h is what? Well, by its definition, it's this integral, which is the area from a to, in this case, x plus h under this curve. So I'm just going to kind of draw it in this way. That's what this piece is. F of x, on the other hand, is just the area under this curve from a to x, which we're subtracting. So that's this area here. So what we have on top of this fraction is just the area between x and x plus h. Okay. Well, this point here is f of x plus h, and this point here is f of x. So this area is approximated by what? Well, it's approximated by f of x plus h plus f of x over 2 times the distance, the width here of this rectangle, which is h. So this is an approximation for f of x plus h minus f of x minus f of capital F of x. So if I substitute that in, what do I get? I get the limit as h approaches 0 of f of x plus h plus f of x over 2 times h over h. Well, we want to evaluate this limit, and it's not that difficult. The h's are just h over h. That approaches 1, so we can ignore them. As h goes to 0, f of x plus h is going to go to f of x. So we have 2 times f of x. So this is just f of x. It's our limit. Well, when we substitute that in here, what does that tell us? That tells us exactly what we want to know. That the derivative of this capital F of x is our function. This is just a dramatically wonderful result. It says that if I want to evaluate an integral, the area under some function, I just need to find its antiderivative and evaluate it at, I guess I erased it, at its 2 endpoints. That's what we did here in this example and in the first example. But apparently this is generally the case. All right, well, we should try a few more of these. It's kind of a wonderful idea. We spent all this time learning about derivatives, and we didn't have to spend that much time kind of looking at them backwards, how to undo a derivative. And now we see that that same knowledge is going to allow us to find these very general areas. So, starting example, let's try and find the integral from 2 to 4 of squared dx. So what do I mean by that? I have a parabola. It's my x squared, my function. And I pick 2 points, 2 and 4. And I want to know the area underneath it. Whereas previously we were limited to polygons, shapes with straight sides, or some limited other number of curves, circles. Now we just pick some arbitrary curve, some function, and we're going to evaluate it. So we're going to evaluate this as the antiderivative of our function from 2 to 4. Well, what's our antiderivative of x squared? Everybody should be familiar at this point. It's a pretty easy one. It's the antiderivative of x squared.
X
Yes.
to the third over
2 over 3. So that means this is 64 over 3 minus 8 over 3, which is just 6 over 3. Wow. We'll kind of go crazy with this stuff. This is great. All right. Try another. Let's look at the integral from pi over 3 to pi over 2 cosine of x. Well, again, it's nice to have a picture of what we're doing. This is pi. Pi? No, that's 2 pi. So where would pi over 2 would be here? Pi over 3 would be over here somewhere. Not drawn scale that well. Okay, so now we're looking for an area under a trig function. Right? So again, we're going to evaluate this as some antiderivative from pi over 3 to pi over 2. So the antiderivative of the cosine, that's pretty easy, isn't it? Yes?
Negative sign. Negative sign. Oh wait, no, positive sign.
Easily remedied. Yes. I always have to kind of, like, which way are we going with sine? Sine is cosine, cosine is negative sign, doing differentiation. But going the other way, you have to be more careful. Okay, so we just have sine of pi over 2 minus sine of pi over 3. It's scratch my head a little. Sine of pi over 2 is 1. Here's my circle, sine 0, sine 1. Pi over 3 is a 60-degree angle, right? So the sine will be, what, square root of 3 over 2? 2 minus square root of 3 over 2, if you like. My notes are all wrong. Oh, well. If we got it right. Okay. Well, we've tried polynomial functions. We've tried trig functions. Why not try an exponential function? Let's evaluate e to the x from 0 to 2. Let's see, what does that look like? Something like this. It's hard to like imagine what, you know, like the excitement that Leibniz and Newton must have felt when they discovered that, all these very exotic functions they'd been dealing with, but didn't know how to compute, areas with edges of these functions. And all of a sudden it was like, hey, everything's possible now. All right, so this must be some antiderivative here that we're going to evaluate this at. I guess it's worth on this example throwing out that when I asked for the antiderivative of e to the x, someone want to tell me what that is?
E to the x?
Well, is it though? Not really.
Constant?
Yeah, there's a constant in there. Use k. And we've been ignoring it, and that's okay. And here's why. I can pick any k I want. I'm just going to leave it k. According to my notation, this is e to the 0 plus k minus e to the 2 plus k. So whatever constant I pick is going to go away. Go back to that graph I drew when I was showing you how we get this. Where we have x and x plus h. I had to pick some point A here. But I could have picked that point anywhere, right? Here. That's my k. And so when I subtract, and I'm just trying to find the derivative here, it goes away. Okay, so what is this? E to the 0 is 1, and e squared is, I did it wrong. Did it backwards. This is 2. This is 0. So that's e squared minus 1, which about 5 or so. where do we go next? Well, what happens if our function just happens to lie below the x-axis? Well, remember when we wrote that original that definition? This delta x was just some, some point on this interval. These are all going to be negative. So we would expect that this integral here, each of the components are negative, so we would expect it's going to be less than 0. So now we have to think a little bit about what we mean by area. Well, the usual meaning of area is like length, it's a positive value. So one way we can think about this is that, yeah, there's a positive area down here, but it's going to be the negative of this integral. This can get a little more complicated. We're going to look at this function a little later. Kind of looks like this. And if we want to integrate this, let's call this f of x. 0 to 3. We're going to run into an additional complication. Is over here, we're above the axis, and here we're below the axis. And if we were just to evaluate this integral, we would get, I guess we could call this area 1, this area 2. We're going to get the value of area 2 minus area 1. Because this is going to show up in our sum as negative area. We'll accept that term for the time being. If we wanted the sum of these as positive areas, we want to rewrite it this way. Asking for the absolute value of f of x. In which case we need to work a little harder to evaluate it. We're going to look at this problem later. All right. So it seems like we need some more equipment to deal with integrals because of these types of complications. Has anyone not seen this before? We all on our second pass here, or is this new to anyone? New? Okay, all right, so let's take a look at one possible situation. here we have some function, and we have 3 points, A, B, and C. And we'll call the area from A to B A1, and the area from B to C area 2. So let me write that out. Area 1 is this integral from A to B of f of x dx. And A2 is the integral from B to C of f of x dx. Well, clearly the entire area is just the sum of these areas. Well, that tells us that if we add these two areas, we're just going to get the area from A to C of the function. So this is our first property of integrals. I think I'm gonna make a list of them. Keep up here. You might see where that might already come in handy in that problem I showed you, the absolute value. We'll get to that. We'll get to that. So I'm going to do kind of a sleight of hand here. I'm going to take that property just going to switch the B's and C's. And these are just constants. They represent something on the picture here. But I'm just going to change this to A to B. That's B to C. This to C and this to D. Is that what I want it to do? Yeah. Well, that shouldn't change the equality, but let's take a look at what that actually means. Integral from A to B, well, that's area 1. The area from A to C, well, that's the whole area, A1 plus A2. And now we're just left with this C to B. Well, okay. So we can remove the area A1. This becomes negative area A2. But area 2 is just the integral from B to C. I guess it would make more sense to put the minus over here. So what this says is that if you integrate in one direction from one point, to another, and here in this case B to C, you just get the opposite if you integrate in the other direction. So again, a useful property of integrals. I think I'm just going to write A's and B's here. Okay, any questions about that? Useful property. Okay, what if I wanted to evaluate this? This is, I'm going to integrate from A to A. Well, I think if you go back to the definition with the sum, it's pretty apparent that this is going to be 0. But we're going to do a little sleight of hand here. This is the integral from A to B. I just pick some arbitrary B. Plus the integral of B to A. Now here I'm using the first property. I'm just finding some point other than A and integrating from A to B and then from B to A, and that's just going to be the same as A to A. But according to my second property, if I reverse the B and the A here, I just get minus what I had before. And these being the same except for the minus sign, I get 0. So that gives me my third property. If I integrate from one point to itself for a function, I'm going to get 0. I think that's a good stopping point for a few minutes. I guess for those of you who weren't here at the beginning of class, I'll repeat myself. I'm working on the midterms. They're not finished, and they won't be finished for a few days. I still need some students who haven't taken the exam to take the exam. So probably sometime next week, they'll come back. Okay. I'm going to take a look at what happens with an integral where we're integrating some function I'll call h of x, where h of x is just the sum of two functions f of x, g of x. And, going back to our original definition, sum of h star of x dx would be the sum of g of x star dx plus the sum of 2 to the third plus excuse me, f of x g of e star times delta x. I'm just here rewriting h of x as g of x plus f of x. This sum we can rewrite. We can distribute the delta. And we can rewrite this as separate sums. Well, when I find the limit of this, of course, the limit laws allow me to break the sum up by the limit. So, of course, I'm going to just end up here with, read it all out, integral from a to b of f of x plus g of x dx is just going to be the sum of these two integrals. X dx plus integral g of x dx. Fits nicely with our whole kind of linear idea of the way limits work, the way derivatives work. Now this is the way integrals work. We can break up sums. So that will be our fourth property. Now, using that formula, I can merely substitute for g of x minus g of x, and I get a new formula that f of x minus g of x is just going to be first integral f of x dx minus integral from the g of x dx. So I'm going to add that to our list, but I'm going to do it in kind of a sneaky way. I'm just going to have a plus or minus here, and a plus or minus here, where you either choose the upper choice plus or the lower choice minus. All right. dx does to this integral. And again, going back to the sum, we have the sum of c f is x star is dx. But I can take c out from this sum. So this just becomes c and again, applying the limits here, we just see immediately that this is just c times the integral. Which does not seem like a surprise. All right. Okay. So now we have some basic properties we can use when we're working with definite integrals that might help us calculate. I want to go back to the problem I talked about earlier. Where you have an absolute value, some function. Now, if the function were already always above the x-axis, you can just remove the absolute value signs and get the value, since this is always positive. The absolute value doesn't change anything. But if instead your function, wanders, you have to differentiate. That was the wrong word. You have to identify which parts of the curve are above and below. So we have some point here, x1, x2, x3, x4. And you can see that the we can just say this is the integral a to x1 f of x, absolute value of x, plus x1 to x2 and so forth. And you can look at each of these and say, well, all right, from a to x1, function is positive, so I don't need the absolute value sign. But from x1 to x2, this area is going to come out negative. I want the positive, so I'm going to have to change the sign here to remove the absolute value sign, and so forth. So I end up getting some of these areas instead of treating them as a negative area. So why don't we do that problem I started with? I wrote this f of x cubed minus 6x, which again looks going to look something like this. To check this, at 0 it's definitely 0, and at 3, it's going to be 9, that's going to be 27 minus 18, so it's going to be a positive value here. But if we set this equal to 0, find its roots, we're going to get x squared minus 6, 0, or x times x minus the square root of 6 times x plus the square root of 6. All right, well, this root minus the square root of 6 is over here somewhere, so we don't really care about that. We really just care about x equals, we don't really care about x equals 0 either, because that's where we're starting. We really care about this point, square root of 6. So here. Okay, so we want to find the integral from 0 to 3, the absolute value of x cubed minus 6x dx, which is the integral from 0 to the square root of 6, the absolute value of x cubed minus 6x dx plus absolute value, the integral from the square root of 6 to 3, the absolute value of x cubed minus 6x dx. This using that the first property. Well, we can see here in this diagram that this first area is below the line, so we can remove the integral sign by putting a minus here. And the second part of the area is already positive, so we can remove the integral sign. Now at this point, it's just a matter of calculating the antiderivative and evaluating it. So let's go ahead and try that. So the antiderivative of x cubed minus 6x is going to be what? X to the 4th over 4 minus 3x squared, 0 to the square root of 6. This is one of those problems where if you're not really careful with your negative signs, you're going to run into trouble, but let's try and be careful here. I don't have to do this again. It's going to be the same, right? X to the 4th over 4 minus 3x squared, square root of 6 to 3. All right. Minus square root of 6 to the 4th, that's 6 squared, or 6 over 4, minus 3 times the square root of 6 squared, that's 3 times 6 minus 18, plus 3 to the 4th is 81, minus 3 times 3 times 6, 27. Okay. 36 divided by 4 is 9. So 9 minus 18 is negative 9. But we have a negative sign here, so it's just 9. And I don't know what we can do with this. 81 over 4 is 20 plus a quarter minus 27. So 29 minus 27 is 2 plus a quarter. So 2 and a quarter. I think I got that right. It's a lot of work. No, I did something wrong. anybody catch an error? Or are my notes wrong? That's possible too. Oh! Yeah, this is kind of like, you have your nose too close to things. It's easy to miss what you're doing. Let me try again. Minus square root of 6, which is 36 over 4, minus 18, minus, okay, 0 minus 0. That's fine. Plus 81 over 4. Minus 27, minus, now we have to subtract this. So, again, over 4 minus 18. So if this minus goes here, it's going to cancel these. And this is going to be 20 1/4. It's 27. That's not right. Oh boy. That's why you have to check your work carefully. I'm not running low on time here, so I'm just going to give it one more shot. Let's do it piece by piece. Let me just do this piece separately. See if that makes sense. Negative x⁴ over 4 minus 3x² from 0 to square root of 6. So that's 36 over 4 minus 27 minus 0. Doesn't really matter. So this is 9 minus 27 or minus 18 or 18. This isn't 27. This is 6 times 3 is 18. This is 9. This is 9. Okay. So that's the first part. Second part is square root of 6, 3. So again, 81 over 4 minus 27 minus 36 over 4, which is 9 minus 18. So 20 1/4 minus 27 minus 9 minus 18, which is minus 9. So minus and minus 9 is plus 20 1/4 minus 27. That's negative 6 3/4 plus 9. So that's 2 1/4. So 9 plus 2 1/4 is 11 1/4. Anyone have a calculator? Nobody has a calculator today. I didn't bring one. All right. Okay, well, lots of math. All right. There are a few more details about integrals we want to go over. First property says that if f of x is greater than or equal to 0 on some interval, then the integral is going to be of f of x dx will be greater than or equal to 0. I think this is quite plausible. Think of some function above the axis. This integral is going to be positive area. However, we could go back to the definition of a sum if each of those partial, pieces of the sum are greater than 0, greater than or equal to 0. Their sum will be greater than or equal to 0. So this is the, I guess I'm going to start my counting over. These are comparison properties. So f of x greater than or equal to 0, on A to B. The integral greater than 0. The second property, which is somewhat related, is if f of x is greater than or equal to g of x on some interval a to b, and the integral of f of x is greater than or equal to the integral over g. Again, that seems pretty plausible if you think about it graphically. F of x is always greater than g of x. You can see the area underneath is always greater. So that's our second comparison. this third property is kind of a direct result of this. If you think of say g of x as the function m, the constant m, and this is just m times b minus a. If, on the other hand, we had this function were some little m, well, this is just m times little m times b minus a. This tells us that if f of x is always between m, little m, big M, some constants, then m times b minus a will be less than or equal to the integral f of x, which will be less than or equal to big M times a minus 3. I guess the way to look at this is you have some function, you have some value big M, it's greater than f of x, you have some another constant, always less than, and this area of our function will always be less than this rectangle, and will always be greater than this rectangle. Now, one stipulation I should make is I've drawn all these diagrams to be nice and easy to understand, so they're all positive. But these properties are true whether f of x is always positive or not. So, where we're at now is this, we have all this equipment. We can find integrals by finding antiderivatives. And there are other ways, even if you can't find an antiderivative, you can use the limit process. So the question is, are all functions integrable? And, and the answer is no. For example, we take this function which is equal to c if x is irrational, but 1 if x is not rational. We've seen this function or something like it before. It's kind of hard to graph it. It's almost constant, at least for the irrationals. But with our current equipment, with our current definition of integral, it doesn't really make sense. We can't find this area. So it might be nice to know under what conditions you can find an integral. I guess we ran out of room over here, so. this way. So, the first condition is conditions for integral, conditions, or I'm just going to say having an integral. F of x is continuous on a b, or as a host of finite number of jump continuities. DIES. Okay, so what are we talking about here? There's this function. I think we sometimes write it this way. It's the greatest integer less than or equal to x. What's that like? Well, from 0 to less than 1, it's 0. And then it jumps to 1, jumps to 2, jumps to 3, so forth. So we could say integrate this from 1 to, say, 1 to 4. And we're not going to go through the usual procedure. We're just going to look at this graph and we're just going to evaluate it. So 1, 2, 3, 4. So we've got 1, 2, 3, 4, 5, 6 squares. The jump discontinuities do not prevent us from finding this integral. Now, here we have a finite number of jump discontinuities. Yeah. So we've satisfied that condition. That's actually the only condition. If this is the case, then integral a to b of f of x dx exists. So that's the condition you have to be concerned about. This is a little different from a derivative, right? You can't have a derivative at a jump discontinuity. Let's try some of these. Okay. Let's start with a basic one. Find the integral. I'm too tired. We lose. Thank you. 2 out of 2. Let's see. Times a charm. Oh boy. 1 to 2, natural log of x. Take a minute and see what you can do with that. No, I'm scratching my head here. Do we know what the antiderivative of the log of x is? I don't think we do we? No. That Rosanna Danny, anyone know Rosanna Danny? Saturday Night Live? He goes, oh, never mind. All right, we're gonna get to that. My apologies. I don't know how to do that. Well, yeah, this will be a little bit better. How about that? That makes more sense. All right. Let's give that a try. Oh, let's see. Doesn't seem to want to work the way I want it to either. Anyone got a value here? Seem it. F of x equals 1 over x. What's the antiderivative? Oh, no.
Natural log.
Hmm?
Is it natural log of x?
Yeah, I guess that is gonna work. Okay, so natural log of x from 1 to 2 is just log of 2 minus log of 1. Anyone remember what the log of 1 is?
0.
0. That's just the log of 2. Well, that's interesting. You could define the log of x, the integral from 1 to x, 1 over x. That is, gonna draw this function 1 over x. And pick a point measure the area under this curve, you get the log of x. That's pretty cool. All right, something a little more straightforward. How about the integral from 1 to 3, x squared minus 2x plus 1. Anyone have the antiderivative for me already? Oh, you're hard at work with the numbers. Anyone? Does that look right? What's that gonna be? Nine plus 3 minus 1/3 minus 1 plus 1. So, if you want to finish, go ahead. You get 26/3. Of course, that function looks like this. Right? So if we wanted to find, you know, guess we could do this, couldn't we? All I'm gonna ask you to do for this one, you don't have to calculate it, just tell me how to rewrite this integral without the absolute value sign. Oh, you know what? I take it back. It's from here. How about that? Where am I going to switch this over from negative area to positive area? At 1, right. You could say x squared minus 2x plus 1 equals 0, but that's x minus 1 squared, so it's at 1. Right. This one I just have a couple more. I don't know if we might run out of time here. Just find this one just really satisfying to know 0 to pi sine of x. So I've got my sine function. I just want to know what the area under that sine bump is. So what goes here? Anyone guess?
Negative cosine?
Negative cosine. So negative cosine of pi minus negative cosine of 0. I know what the cosine of pi is. Cosine of 0 is 1. Cosine of pi over 2 is cosine of 2 is 0. Cosine of pi is negative 1. So that's 1. Minus, minus, plus, plus. Cosine of 0 is 1. It's just 2. Strange curve with the strange numbers, with the area under its 2. All right, we'll get enough practice with these. You're not gonna do it, but you might want to, try this on your own. Because again, it's so satisfying after all these years. What is the integral, 2 times the integral from 0 to 1 square root 1 minus x squared dx? What is this? What is this area here? Anyone? Any idea? Oh, I'm sorry. Negative 1. F of x equals square root of 1 minus x squared. F of x squared equals 1 minus x squared. Or f of x squared plus x squared equals 1. So if I put y in here, does everyone know what that is now? Just a circle. So if you integrate this from here to here, integrating this area, and if you multiply it by 2, you should find out what the area of the circle is. Okay, thank you.